First up, we're going to have Benoit Montague telling us about abstract interpretation for higher order programs.
Hello, my name is Benoit Montagu, and I'm going to tell you about a joint work with Thomas Jensen about the abstract interpretation of higher order programs. The problem we're interested in is the inference of program frames. This means that we want to detect what a function call does not change. For imperative programs, it amounts to finding which parts of the global state are not modified by a function call. For functional programs, it amounts to finding which parts of the input and the outputs are the same. This frame information can be used, for example, in optimizing compilers to perform common subexpression elimination across function calls. The same information can also be exploited in program verification and in particular invariant preservation proofs. The properties of the parts of the state that have not changed are indeed automatically preserved. Last year, we published a paper on what we call a correlation analysis. It's a static analysis that infers frames for first-order programs. We applied it to the verification of an OS microkernel, and it was able to prove automatically 68% of the invariant preservation lemmas. That means that inferring frames is really useful in practice. In this work, we want to extend the correlation analysis to infer frames for a higher order language. Our long-term goal is to integrate such an analysis in a general-purpose proof assistant to make the verification of large programs easier. To infer frames for the lambda calculus, we followed the methodology that is offered by the abstract interpretation framework. The first step is to clearly define what property you're interested in. In this work, we want to find relations between the inputs and the outputs of a lambda term. The second step of the methodology is to define a collecting semantics for your property. It describes how your property evolves when your program gets evaluated. In this work, the collecting semantics takes the form of a denotation of a lambda term into input-output relations. We have proved that this denotation is sound and complete, and as a bonus, you will find in the paper an equivalent definition in the form of a program logic. The third and final step of the abstract interpretation methodology is to apply successive abstractions on the collecting semantics. By doing so, you obtain an analysis with which you can effectively compute. In this work, we have used two abstractions. The first one is a variant of a well-known independent attribute abstraction, and the second one introduces the correlation domain we presented last year that we extended to support first-class functions. What we get in the end is a simple modular analysis that is already quite expressive. And we have mechanically verified all these results in the Coq Proof Assistant. The language we study in the paper is the n-typed call-by-value lambda calculus extended with pairs and binary sums. The definition of values in this language is the standard one, and we use the standard small-step semantics for call-by-value that performs a substitution to reduce a beta regex. For this higher-order language, we want to infer relations between the inputs of programs and their outputs. But what are the inputs? Consider that the inputs of a program are the possible substitutions sigma that assign values to the free variables of that program. Then the input-output relation of a term t for a set of inputs I is the set of pairs made from substitutions drawn from the set of inputs and the values that are obtained from evaluating the term t sigma, that is t where all its free variables have been replaced with the values defined by the substitution sigma. With this semantics of input-output relations, we can, for instance, state that a term t always returns 0 when the input x is assigned to a negative value, or that t returns a value that remains above the value of the input x. Now we remark that if sigma defines all the inputs of a program t, then you can use any substitution sigma prime that defines more inputs, even some inputs that are not necessary to t, without changing the meaning of the program t. In such a case, we say that sigma prime extends sigma. And because specifying values for more inputs than necessary does not change the meaning of a program, we can actually close the set of inputs I under the extension ordering of substitutions. And by doing so, the input-output relation of a term becomes what we call a stable relation. A relation is stable when, if an input substitution sigma is related to some output v, then any substitution that is more defined than sigma must also be related to the same value v. This definition should not surprise the logicians among you. What we call stability is similar to the notion of persistence that is found in Kripke-style semantics. That is to say, if a property holds in some world, it must also hold in any larger world. And that definition should be no surprise to the semanticists among you either, because a stable relation is in fact a monotone function from substitutions ordered with the extension ordering to sets of values ordered with set inclusion. So we have defined in the paper a denotation that, given a term t and an environment, builds a stable relation between the inputs and the outputs of t. The environment denotes a set of admissible inputs, and as expected in denotational semantics, the denotation function is defined in a compositional way by induction over the syntax of the program. For example, the denotation of a program that builds a pair out of two subprograms T1 and T2 is the pairing of their denotations. Here, the pairing of relations relates an input sigma to a pair of values, where the first component of that value is related to the input using the denotation of T1, and the second component of the value is related to the same input using the denotation of T2. We have proved that this denotation is sound with respect to the input-output in the sense that it is an over-approximation of the input-output relation. This means that if you take an input substitution sigma in the set of valid inputs described by the environment, and if the evaluation of the program T with these inputs gives you an output value V, then the input-output pair sigma V is predictably in the denotation of the program. Interestingly, the denotation we have defined is also complete. This means that the denotation of the input-output relation are the same. We have mechanically verified these results in the Coq proof assistant. Our denotation must treat variables very carefully, and here is why. You should expect that the denotation of a variable is just a lookup for that variable in the environment. This is indeed a correct over-approximation. But in the paper, we give a sound and complete definition. Here it is. I will not explain all the details, but just notice that the definition uses a relation self of x. This relation states that the output must be exactly what was given as input for the variable x. In particular, this means that the denotation of the variable x is a relation in which the variable x occurs. In other words, the denotation of a term may involve the names of its inputs. This means that the semantic denotations can refer to syntactic variables. This has consequences on the well-formedness of the definition. You need to show, for example, that the free variables of your denotations are included in the variables that are defined by the environment. But what does it even mean to be a free variable for a relation? Relations are semantic objects, not pieces of syntax. And to answer this question, we use nominal techniques to carefully handle names. If you want to dive into the details, please have a look at the paper. Now, how do we handle functions? Let's start with function application. The denotation of T1 applied to T2 is the app of their denotations. This is a relation where when you take values in the denotations of T1 and T2 and apply them together, you must obtain a term that evaluates to a value V. And this result value V must be the value in the final denotation. That's it for applications. Now for functions, I won't have time to show you the full definition of the denotation, but you should remember that it can be over-approximated by a relation that, assuming some condition R on the argument, gives you the denotation of the function's body. Here is the unfolded definition, where I have chosen to hide some pieces related to name management. Let's go through it. This is a relation where the output is supposed to be a function, for which we will consider all possible applications. When we apply this function to an argument v1 that satisfies the condition R, if the evaluation gives a result v2, then v2 must be in the denotation of the function body. But the argument and result must be valid for all possible extensions of the input substitutions, as is usually found in Kripke-style semantics. And this is essential because this quantification over extensions of the inputs is the reason that makes the definition a stable relation. In the end, we have a modular denotation rule for functions that we later use as a basis for the modular analysis of functions. So we have defined this denotation, this collecting semantics, that describes exactly the input-output behavior of programs. And we used it as a starting point to build a static analysis. So following the abstract interpretation methodology, we applied successive abstraction steps. So far, our denotation tells us how the inputs are related to the outputs globally. We first apply a variant of the independent attribute abstraction. We obtain at this point what we call pointwise relations that tell us how each input is independently related to the output. For each input x, we obtain a binary relation on values that says how sigma of x is related to the output v. Then we abstract these binary relations on values into an abstract domain that we call correlations, and with which we can effectively compute. This abstract domain is an extension of the correlation abstract domain from our previous work that we extended with first-class functions. You will find plenty of details on how we did this in the paper. We implemented the resulting analysis in OCaml. This is a bottom-up modular analyzer that analyzes functions only once. For every function, it computes a function summary that approximates the extensional behavior of that function. The analysis was really not designed to compete with existing control flow analysis, and it does not compete. Still, it can give very precise results, even though it follows a fully modular approach. Let's consider this classic CFA example. This program calls the identity function twice on two different arguments and returns the result of one of the calls. It's an example where 0 CFA is not precise enough and 1 CFA is required to achieve good precision. The analyzer first computes a summary for the identity function. The summary tells us that this is a function whose result is equal to its argument, whatever is the calling context. This summary is instantiated once for the first application. We get that y1 must be bound to the first injection. Then the summary is instantiated a second time for the second application. And the analysis tells us that y2 must be bound to the second injection. Finally, the analysis for the result is the domain we have obtained for y1, that is to say, it has to be the first injection. On this example, we can see that the analysis gives the most precise results, and this is on par with 1 CFA. To wrap up, we have defined solid foundations for the relational analysis of higher order programs by means of a sound and complete relational semantics for the lambda calculus. We exploited this collecting semantics to design an effective analysis, and we provide an artifact for the Coq formalization of the theoretical development. As a long-term goal, we would like to integrate such an analysis with a proof assistant to reduce the proof effort for the verification of large programs. On the shorter term, we want to support more language features and to increase the precision of the analysis, for example, by exploiting numeric abstract domains. Finally, we are convinced that our denotation semantics can serve as a basis for the future design of novel relational control flow analysis. That's all. Thank you for watching.
Thanks, Benoit. If you're watching in the New York time band, you should now see a link appear in Clowder to join a video chat where you can ask Benoit your questions. Unfortunately, he's not available in the Asia time